Our next speaker is Dr. Gregory McIsaac, with 40 years experience in research, teaching, and outreach on topics related to nutrient cycling, runoff, and drainage from Midwestern Ag Systems. Earned a PhD in Ag Engineering from the University of Illinois, Urbana-Champaign, and retired from a faculty position from the Department of Natural Resources and Environmental Sciences here at the U of I. Since 2013, he has contributed to the Illinois nutrient loss reduction strategy, primarily by calculating and analyzing nutrient loads in the state's rivers. In addition to an NREC-funded project on phosphorus in the Illinois River, he is also collaborating on projects examining phosphorus levels in the Sangamon River, that's funded by the National Science Foundation, and nitrate in the Rock River, funded by Illinois Corn Growers Association. So please welcome Dr. Greg McIsaac.
Good morning, everyone. Thank you for your time and attention. And let's see if I could work the system here. I'd like to acknowledge my co-authors, collaborators on this project. Tim Hodson from the U.S. Geological Survey, Amsila Marcus, who's here, who's mentioned earlier, Rabin Badarai, who's also here from Ag and Biological Engineering, and Daniel Kim, who's also from Ag and Biological Engineering. So we have funding from NREC as well as a cooperative agreement with the U.S. Geological Survey to do this work. This is work we've been collaborating on for the last year. So we're happy to try and explain it and get your feedback. So one of the motivations for this project is the fact that across the state, Illinois River carries the lion's share of the phosphorus. It's also the biggest river in the state, and that's part of the reason why it has most of the phosphorus, but it also, in absolute terms, it also increased. So in this graph, you see a series of colored bars, each one representing 1 million pounds per year. Our scale is in million pounds per year. So the black bar is the baseline period, that's 1980 to 96, and that's what we're benchmarking our progress against. And the red bar is 2015 to 19, and you see there's a 30% increase from the baseline to that last period. And in fact, from all but one of the rivers, there was an increase in phosphorus loss. But the Illinois River was the biggest in absolute terms. And also we knew that up in the Chicago region, the Metropolitan Water Reclamation District had reduced some of its discharge, and we were expecting to see some of that benefit coming downstream, but it didn't show up. We're actually going in the opposite direction. So one of the motivations for this study is to figure out why that happened. So our objectives were to identify and quantify factors contributing to the increased phosphorus loads in the Illinois River at Valley City. That's the furthest downstream monitoring location. And what we did was we calculated the loads for different time periods and different sub-watersheds. We did this for about 40 different sub-watersheds within the basin. And then try to identify factors that might explain both the variation in time and space. So we have the water flow data comes from the U.S. Geological Survey stations. Most of the water quality data comes from Illinois EPA, where they sample about 9 times per year. But there's also places where the U.S. Geological Survey also samples. So we have additional sampling from USGS. Load estimation is done with a system called weighted regressions on time, discharge, and seasonality. It's developed by USGS. And it's a newer version of that process that Tim Hodson is an expert on. And so in addition to phosphorus, we looked at other nutrients or other constituents, including suspended solids, volatile suspended solids, chloride, sulfate, nitrate, and total suspended solids. And we also looked at dissolved as well as total phosphorus. We have point source data from MWRD that's serves almost all of Cook County, and their data goes back to the early 80s. Also, the Sanitary District of Decatur shared some of their data that go back to the early 90s. And we also have some data that doesn't go back quite that far from the EPA NPDES permit system. We also have land cover data, crop production, tillage, fertilizer, population. And there were some older, we consulted some older estimates of point source data, but we ended up not using that because it actually was not very consistent with the actual data that we got from some of the dischargers. So these are a map showing our results from those 40 different subwatersheds. This is the early period, 1989 to 96. We wanted to get the full baseline period, which is 1980 to 96, but a lot of the data for these locations didn't go back to 1980, and the best coverage we could get is from 89 onward. So the red colors, so all these are in total phosphorus yield. That's a loss per unit area. It's in metric units of kilograms per hectare, which is very similar to pounds per acre. It's slightly larger than the pound per acre. So if you think of it as a pound per acre, you're not far off. So what stands out here, the deeper reds are the higher yields, and that you can see the Chicago area is the deepest red areas. But then you got this blue area in the middle, that's from Marseilles down to Valley City. So the blue is actually where there's more phosphorus leaving the system than is coming in. So we're at that time period, accumulating phosphorus in that section of the river basin, which includes the river itself, but also includes the drainage area around that section of the river. So why would that be happening? This section of the river is very flat, and the Water Survey has been monitoring sediment yields and loads throughout the basin for many years, and they've reported that this section of the river accumulates sediment. You have more sediment coming in than is leaving, and I think people that live in that region are aware of accumulations of sediment. And a lot of phosphorus is transported with the sediment, and so it makes sense that phosphorus would also be accumulating in that section of the river. So now, fast forward to the 2015 to 2019 period, same data, or the same phosphorus yields. You see Chicago area is still very high yielding in phosphorus, but the blue area went away. So that section of the river is now exporting phosphorus rather than accumulating it, or accumulating as fast as it did in the early period. So that's a big part of why we've had an increase at Valley City. So in addition to increased loads total phosphorus loads at Valley City, we're also seeing increased dissolved phosphorus loads. So more of the phosphorus that's coming in, and this is true pretty much across the board. We're getting more dissolved phosphorus, less particulate phosphorus. That's mostly attached to sediment. And we're also getting less suspended solids loads, which is primarily sediment. So that's kind of an indication, or maybe a consequence, a reasonable consequence of farmers adopting conservation tillage. So it's reducing the amount of sediment and phosphorus attached to sediment that's coming down the waterways. But because you have less incorporation of phosphorus into the soil, when you do get runoff, you tend to get more dissolved phosphorus in the running off the fields and in the rivers. So now this is the change from the first period to the second period. Now you see a lot of blue colors. That's where we actually have achieved a reduction in total phosphorus loads in the river, or yields in the river. And it's in the Chicago area, even though there's still very high yields from the Chicago area, there has been some reduction there. But now you see the biggest increase is in that section of the Illinois River from Marseilles down to Valley City. There's also an increase, for most of the tributaries, there really was not much change. The one exception is the Sangamon River, where there was an increase of about 1.3 million pounds per year, and that is based upon another project I'm involved with. It's primarily coming from the Sanitary District of Decatur. It's not just their municipal wastewater, they also treat industrial wastewater from ADM, which has a very high phosphorus concentration. So in that middle or lower section of the Illinois River where we're seeing the big increase, that's, the increase is 4.6 million pounds per year, and that's roughly the same as the discharge, annual discharge from the Metropolitan Water Reclamation District in Chicago. So it's essentially equivalent to 5.2 million people, wastewater from 5.2 million people. So it's a large, very large increase there. And most of it, and then when you add that to the Sangamon River increase, we have a total of increase at Valley City of 6 million pounds per year. So looking at what might be driving that in to some degree, we divided up the subwatersheds into those with high developed or based upon the percentage developed area, meaning urban area. So these urban areas that are shown in blue, those are more likely to be impacted by point source discharges. And so the scales here, the bottom scale, water yield, and that's river flow divided by drainage area, and it's directly directly comparable to rainfall. It's how much of the rainfall runs off, and it's in metric units in millimeters per year, and 100 millimeters is about 3.9 inches per year. You see, and the 9% cutoff, that's sort of somewhat arbitrary. There's not a theoretical reason why 9% would be different, but it just comes out when I examine the data at different percentages, and you see this clustering of points in the middle that kind of fall on a straight line. So those are the more agricultural basins, and as we might expect, there's a tendency as the water yield goes up, you get higher and higher change in phosphorus yield from those places. Whereas the blue, where you've got increases, where you've got input from point sources, that's pretty unrelated to the change in water yield. And I could point out a few different places that are actually have achieved a fairly large reduction. And one of those, the one on the bottom is the Thorn Creek watershed. See if I can do this right. So it's the blue, the dark blue. It's a small little watershed. It's actually in Cook County. It's the one part of Cook County that is not served by MWRD, and they made a fairly large reduction in their yield, total phosphorus yield. Excuse me. And that was despite increased rainfall, increased water yield. So, and then the one on the top there says Mars to VC, that's Marseilles to Valley City. That's one of the more ag watersheds where you have a high, it was one with the biggest increase in phosphorus yield. But that line might suggest that it's related to increased water yield, but actually in that particular case it's not, because if you look at, so here we're looking at, on the left graph, this is the total phosphorus load leaving Valley City and subtracting off what's coming in from all the tributaries and from the upstream watersheds. And it's plotted against the related water flow. So it's the water flow at Valley City minus what's coming in from upstream. And there's really no correlation there. What we think is happening is that at high flows, you get out-of-bank flow. So the sediment and the phosphorus ends up in the floodplain as opposed to moving downstream. And we see the other graph is simply showing the other, the same basic relationship, but rather than looking at just the flow coming in or the net flow in that lower section of the river, it's looking at the entire flow at Valley City and get the same basic lack of relationship with increased flow. So something other than increased flow is increasing the loads at Valley City. So one possible explanation is that because more of the phosphorus that's coming in is in the dissolve phase, more of it or less of it is getting deposited in the river and is simply moving through the river. And this correlation is consistent with that. So what I've plotted here is the percent or the load at Valley City as a percent of the load that's coming in from upstream, from those all the upstream tributaries of that section between Valley City and Marseilles. And the bottom scale is the ratio of dissolved to total phosphorus. So it's a fraction of the total phosphorus that's in the dissolve phase. As that goes up, then we see a greater percentage of the total phosphorus that's coming from upstream actually achieving or getting to Valley City as opposed to depositing before that. So at 100%, there's no net gain or loss in that section of the river. And above 100%, there's a net source from that section of the river. I shouldn't say just the river. It's the river plus the drainage area around it. And then if it's less than 100, that section is a sink of phosphorus. I should point out that correlations don't prove cause and effect. I mean, there's a correlation, we could tell a story about it, and there's other correlations that might also be involved. And so one of them that jumped out at us is this correlation with chloride. The amount of chloride, mostly coming out of the Chicago area, has been increasing over time. It's a combination of road salt, might also be more people using water softeners. And so there's this correlation, there's correlations between chloride and this dissolved phosphorus to total phosphorus ratio. So there may be a role for phosphorus in helping to desorb phosphorus from river sediments. That's something that needs to be explored. There's also changes in sulfate. Because of reduced sulfate emissions from coal-fired power plants, there's less sulfate deposition on the land, and that's reducing the sulfate in the rivers. And that's changing the ionic strength of the solution, and that can also influence desorption. There's also a decline in nitrate concentrations. The nitrate loads have increased in the Illinois River have increased only about 3%, but the flow has increased quite a bit more than that. So that leads to a dilution effect, and that also influences the redox potential that influences desorption. So all of those factors need to be studied a bit further. With more manipulative type of experiments, when you're trying to explain what's data that's already been collected, you can tell a lot of different stories about it, and so you have to check those stories against experimental data. So just to summarize and conclude, we've got increased phosphorus at Valley City, total phosphorus at Valley City. 78% comes from the section of the Illinois River and its drainage area between Marseilles and Valley City. And then 22% comes from the Sangamon River. So, and possible causes for this increase in load include increased dissolved phosphorus that's less susceptible to deposition along the river, desorptions from river sediments, and that's possibly enhanced by changes in water chemistry. And one thing I didn't mention, there could be a point source. We did spend some time looking at point source data along this section of the river, but none of it added up to that 4.3 million pounds, which is similar to the size of the discharge from Cook County. So, and then in many watersheds, dissolved phosphorus loads increased, while particulate phosphorus and total suspended loads decreased, and that's a possible signal from adoption of conservation tillage. Total phosphorus load reductions in tributaries draining Cook County were offset by increases in the suburbs. I didn't get into this in the discussion, but we did see some reductions in the Chicago area, but increased total phosphorus loads in the suburb areas where there's been an increase in population over that time period. There's also one agricultural basin in that region also had an increase in phosphorus loads at the Maison River Basin. So that offset whatever increase occurred from the Cook County wastewater dischargers. So in agriculture watersheds, with those with less than 9% developed land, the changes in phosphorus loads were weakly correlated with changes in water yield. And so in terms of following up on this, I think there's some room to do some, investigate further the factors that influence the desorption of phosphorus from sediments, as well as the mobilization of sediments in the river, including things like water chemistry and groundwater flow. I think there's also, I think, a good opportunity to look at the particular subwatersheds where we saw either a large increase or a large decrease in phosphorus yields and try to figure out why those were occurring. And with that, I'll just say thanks and answer questions.
Thank you. Really enjoyed your presentation. I just have a question. Do you think that the increase in phosphorus loss could be tied to climate change and the longer time that soil could be saturated, causing phosphorus to dissolve from the iron in the soil?
Yeah, sure. I think that is a potential pathway. It's not one that I've studied closely, but and it may show up more in the agricultural basins. Like in this particular basin, a lot of our monitoring sites were more impacted by point sources rather than agriculture. But it's a good follow-up, good thing to follow up on.
Do we assume the particulate phosphorus is primarily coming from erosion and soil runoff, and that the particulate's coming out of the tiles? And can we correlate the amount of tile in each watershed with any of these figures? Trying to decide how to treat this. Do we need to be worried more about the tile or more about the surface runoff and how it's getting there, and the treatment situation is going to be different? So has that been done, or can you tell anything? Do you have an opinion on that?
I don't know that it's been done. I think it could be done, although one of the problems with correlating anything with tile is that there's not good data on where tiles are located and how intensive they are. And also, the other factor, another big factor that influences the phosphorus loss is just the land slope. And so there's one of the challenges of trying to figure out where the phosphorus is coming from, especially at this huge scale. This watershed covers pretty close to half the state. And so you got to just have a lot of variability across the state. And it probably would, doing that kind of work on a smaller scale is probably a more reasonable approach.
Each one of these stations, did you have 9 samples
Per year.
during the year?
Most of them, yeah. A few of them, there's more frequent, but mostly it's 9 per year.
And then is that figured out ahead of time what days you're going to do those, or is that random, or?
It's more random calendar year based. data that goes back to the 1980s, or even some of it goes back to the 1970s, that it's a system of sampling that the Illinois EPA developed and maintained for all those decades.
Because what I'm thinking is that, after we heard Dr. Ford and, if you have a huge rain event, and you sample upstream one day and then a few days later you're sampling downstream, then maybe those numbers are being skewed downstream because of the water coming down. And it just seems like to me, and I know it'd be a huge undertaking, but you would almost want to be sampling on a weekly basis or something to really get a good hold on what phosphorus levels are.
Yeah, I'd agree with that. So you miss a lot of storm events with that infrequent sampling, and storm events are really important. But that's part of what that weighted regressions on time, discharge, and seasonality attempts to address. So you fit the data you have to the season, flow, and time that it was collected, and that tries to fill in those gaps. And I did do a comparison of, so Lowell Gentry, who's here, he was here, he has a data set where they have much more frequent sampling on the Embarrass River. And I used that approach both with his more frequent data and the less frequent data, and got very similar answers, at least for most years. So I wouldn't, any individual year in our data set probably has a lot of uncertainty to it, but when you average over several years, I think that gets reduced. But it's a good point about
So WRTDS, I think that's acronym for the weighted regression.
Yeah.
That usually requires quite a large sample size as far as the number of samples over the decades. Have they improved that to deal with smaller sample sizes, or, has there been any adjustments made to that in the last 5 or 6 years for dealing with like sample sizes of 60 or 80 or less than 200?
I'm not sure about that.
Okay.
But fortunately, the good thing about even though our data are infrequent, we have a long enough record that it fits the criteria of WRTS. The version that we're using is a recent update, but I don't know if it is designed to deal with smaller data sets.
Okay, I didn't know if they had made, I know they have had updated versions of that. I didn't know if they had done anything to update that aspect of it. The second question I have is, based on your presentation, it looks like there could be a significant amount of phosphorus in the bed load of like the larger rivers. Do you know, as a USGS or anybody, the Corps, anybody taking samples in the bed of the Illinois River? Do we have that data? Has it been collected?
No, I don't know. It's not something we spent a lot of time looking for, so it may be there, and I know that USGS is involved in this fairly intensive monitoring of the Illinois River. It's just getting underway now, so if they don't have the data, I'm sure it's a high priority for collecting.